I am going to talk about something a little bit different today than I would have in previous presentations. But it starts in the same place, and that is the dream of crystal design. It was enunciated by Richard Feynman, who, by the way, has over 1 million followers on Twitter, if you're interested. And in his famous series of lectures, where he is best known for coming up with the term, "there's plenty of room at the bottom," he asked this question: what would the properties of materials be if we could really arrange the atoms the way we want them? And his answer was profound, and it's what has driven impetus in the field of crystal engineering. He suggested that we will get an enormously greater range of possible properties that substances can have and of different things that we can do. And this is going to be the emphasis: different things that we can do, because the way we're doing things today is not working out. We have to change, and the only way we're going to change is with better materials, or as I like to say, secret sources for particular important global challenges. Where we stand today is that crystal engineering is the field of chemistry that is no longer just the design, which was the goal when it first started 50 years ago. It's now the design, properties, and applications of crystals. We know what the important global challenges are. There are more than 4, but these are the 4 where the secret sources are needed. They don't yet exist. Better and cheaper medicines, more efficient solar energy harvesting materials, cleaner access to clean and pure water, and the one that I'll be focusing upon, industrial commodity purification, including carbon capture. Now, normally I would be talking about co-crystals, so I'll do 4 slides in 2 minutes to summarize where co-crystals came from and where they are today. They certainly would be regarded as long known but understudied. They can be classified as molecular ionic. First examples going back to 1841 and 1783 respectively. In the context of pharmaceutical co-crystals, there were examples before the 2000s, but things really took off when these 4 papers were published within a year of each other in around about 2003. Ern was the corresponding author on one of them. The Purdue group associated with SSPC was the author of another, and 2 of those papers came from my group at the University of South Florida. All 4 papers started with the same first 2 words: crystal engineering. Finally, we're designing crystals from the ground up, in this particular case, co-crystals. The rest of the story is that interest continues to grow. This was updated just in the last week. The number of publications on co-crystals is now around the order of 500 a year, and around half of them are on pharmaceutical co-crystals. But as I just mentioned, ground zero in this context kind of goes back to 2003, 2004. And today, where do we stand? There were a few, I think, accidental salt reactions that resulted in co-crystals that happened throughout the 80s, 90s, and 2000s. But in 2015, there were 3 pharmaceutical co-crystals approved by the FDA. 2 of them are very large selling, blockbuster drugs, Entresto and tenofovir alafenamide, which is a co-crystal of a carboxylic acid. And there are more and more pharmaceutical co-crystals being approved, both by generic companies, for generic companies, in order to avoid a crystal form patent, and by innovative companies. Anyway, segue, sort of, not really. Now the subject of today's lecture, which is sustainability in the bigger sense. And I first became intrigued, I should say, and interested in sustainability because of geography. I was standing at a very interesting part of the world this is a clue as to where I was. So if you don't know where this is the Cape of Good Hope. You have the Atlantic Ocean on this side, you have the Indian Ocean on the other side, and it's one of the most pristine places in the world, and they have a CO2 monitoring station there. And I happened to look at a plot that was there that they kept on updating that was about the increase of CO2 levels in the atmosphere. This was in around about 2006 when I visited Cape Town and went to this particular point. At that point in time is when I didn't switch, but I started a program in carbon capture, thinking that I'm worried about my grandkids, because at this rate, it's still going up at 1 or 2 ppm per year. It's going to be a long while before we get well into the 400s. Well, this was up to date. This is where we are today. And it looks, well, it's not a first-order plot, and it's not a linear plot. Things are actually getting worse, and they're getting worse in a hurry, but it's not obvious when you look at the long-term plot. In the 1960s, the rate of increase was about 0.7 ppm per year. In the 1990s, it was around 2 ppm, and this is when things started getting interesting. Right now, we're already up to 3 ppm per year. And so we've seen really a dramatic increase in the rate of increase of CO2 in the atmosphere consistently over the past generations. And there are effects. Some of you might have followed the news and heard that July 2023 was the hottest month ever on record. Well, it's more than that. 2023 is the hottest year ever on record. And by the way, this is not color-coded by temperature. It's color-coded by year. So the blue ones are the 1880s, blue-green is 1900s, and what you can see is it's a steady, gradual increase in the average global temperature, normalized to 0. The scary part is that July 2023 wasn't just the hottest. It was the hottest by a long way over the previous jump, over the previous record, all of which were in the past 5 years. So we really are potentially, even though people are naysaying, reaching some kind of tipping point in that we're losing control. The 1.5 degrees, by the way, is over. Now, the other thing is I said to myself, okay, when the proverbial poop hits the proverbial fan, what am I going to do? Well, I used to live in Nova Scotia, and I thought, I'll just go hang out in Nova Scotia. It rains all the time, never had any issues with forest fires. I lived there 13 years. 2023 was the year Nova Scotia had a problem. August 2023 is when Hawaii had a problem. It turns out I love Lahaina. I go there every year. I have a timeshare in 2 miles away from Lahaina. This was our boat ride in May of this year, and you know what happened this month. Lahaina was turned into what looked like the outcome of a nuclear bomb being dropped on Lahaina. And the boat I took was from that dock right there, and it's now at the bottom of the harbor. So suddenly, I'm not as optimistic as I used to be. I've always had this feeling science will always solve problems, but this isn't just science. This requires government, industry, society as a whole to take this matter seriously. And that part I'm not yet seeing happening. So what are we focused on in my group? In general, the energy cost of gas and vapor purification. Why is that important? Well, the chemical industry, excluding pharma's around $1 trillion a year. The chemical industry has a turnover of around $4 trillion per year, which is about 4.5% of global GDP. And the reason we're interested in gases and vapors is that we're in the age of gas. The age of coal is gone, the age of oil is gone. We're now in the age of gas. Methane is the primary feedstock for the chemical industry. And the initial products are all gases and vapors. It turns out that 40% of the energy used by the chemical industry is for separations and purification. If that's a distillation tower and that's a person, that's using a lot of energy. Around 10% of the world's energy use is the chemical industry. So it's 4.5% of global GDP. It's around 10% of the world's energy use. In addition to purification, there's also gas storage, natural gas and hydrogen. There's also greenhouse gas remediation, which is carbon capture and sequestration or utilization. And last, and I don't think least, because there's no plan B for water, there's water capture, purification, and dehumidification. Dehumidification, by the way, is the biggest energy component of building HVAC. It's not cooling and heating, it's dehumidification. And water capture, purification, dehumidification is another 10% of global energy. So the approach we're taking is called regeneration optimized sorbents, or ROS materials. We weren't as creative as you might think because, in fact, the first compound we studied was a summer student whose name was Rebecca O'Sullivan, and so we called it ROS, and ROS 37 was our first interesting compound. So then we went and retrosynthesized the jargon. Oh, well, let's just call them ROSs, regeneration optimized sorbents. So what is the challenge here with sorbents? Why don't we yet have the secret sources? Well, when it comes to sorption, there are really two alternatives. Physisorption, which uses low energies because it's based upon non-covalent forces, but therefore typically results in low selectivity. So capturing trace gases and vapors, impurities, is not easy using physisorbents. Chemisorption is plan B. And chemisorption, most carbon capture processes now are based upon chemisorption. But there's a problem with chemisorption. The bonds are stronger, so they're harder to recycle. They need more energy to recycle. And they're typically slow. If you're dealing with trace reactions, chemical reactions, the lower the concentration of the reactants, the slower the reaction. And I'll get to breaking up is hard to do, and you can check out any time you like in a moment. What we really want is a sweet spot of properties. Something like a strong physisorbent, but stronger than anything that was seen before, or a weak chemisorbent, which is weaker than normal chemical bonds, somewhere on the order of 45 to 60 kilojoules per mole, but also selective, not for everything, but for the target compound that you're interested in. So the goal is really quite simple. It's going after this sweet spot of energetics. The solution is crystal clear, just as the problems are crystal clear. Now, these songs were written about sex, drugs, and rock and roll, but I can borrow the lines from them. Breaking up is hard to do, and you can check out, but you can never leave. The solutions are let's get physical. And I did an interview on the radio, and they actually played that song at the end of my interview, which I thought was kind of cool. Or we can go for Mick Jagger. You can't always get what you want, but if you try, sometime you'll get what you need. So that's the approach we've been taking. We didn't have a preset agenda. We weren't pushing our compounds. We want to find the best material. Modeling, by the way, one of the reasons I'm a believer in modeling, more than a believer, an acolyte of modeling, is that it can provide critical insight into how to go about making these secret sources. I don't do the modeling, but we've been fortunate enough to collaborate with Brian Space since the mid-2000s. This was a hypothetical experiment where then the hydrogen storage was the challenge. And we were going after, hypothetically, if you had 4 benzene molecules and you put them around a hydrogen, what would be the energy minimum for binding that hydrogen? And the result was actually extremely insightful, even though it was impractically useless for everyday use. And it told us how important the pore size is. It's not just important, it really, 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 really matters. Why? At 3.1 angstroms, which is the van der Waals surface, your energy is somewhere between 11 and 14, the binding energy, 11 and 14 kilojoules per mole. At 4 angstroms, it's half of that. And at 4.5 angstroms, it's a quarter of that. So if you're not in the sweet spot, the energy minimum, you're not going to be able to get these strong physisorbent binding energies. We published more than 50 papers with Brian Space. I like to call him Space Group 231. He just calls them the Space Cadets. And just earlier this year, we reunited in Colorado, a beautiful part of the world, at a Telluride conference. So I'll summarize 15 years of my career that is non-SSPC related, and that was funded by my SFI Research Professor Award, where we developed new sorbents that did things differently, did different things. How did we do things differently? We found these energetic sweet spots in narrow pore, ultramicroporous materials. So we crystal engineered just the right pore size, not big pores, but small pores that are a good fit for the target. And these 4 papers, all very high profile papers, set new records by more than an order of magnitude. So they weren't just better than anything that came before, they set new orders of magnitude for the improvement in the binding selectivity for one molecule over another. Now, at this point, you'd think the problem is solved, but of course it isn't, because there are 10 other things you have to worry about to develop a real process with a real material. And in particular, these are only binary gas mixtures. The real world is non-binary. Finally figured that out. It took a while, but the real world is non-binary. No gas mixture is just 2 components. There's a lot of things floating around out there, especially water, which is both the problem and a solution. Because if you can control water absorption, you can produce pure water anywhere, because there's enough water in the atmosphere everywhere in the world at all times. So I would consider this the single most important global challenge. We take it for granted, especially in Ireland. But water harvesting is not just desirable, it's urgently needed because of the serious water shortages that are present in most of the developed world, including half of the United States, most of Africa, most of Australia, all of India, much of Southern Europe, and northern China. We're facing an imminent crisis, and by the way, we're not going to solve it ourselves, because only 8% of the world's water is for domestic use. Most of it is for agriculture, and a fair proportion also for industry. So the approach we're taking with sorbents, which are now called desiccants if they capture water, is to not go after where most of the water is, which is in groundwater, ice, glaciers, or snow, or rivers, lakes, and reservoirs. It's in the atmosphere, which only has 0.04% of the world's water, but that's still an awful lot of water. It's also inherently renewable, because if you take it out of the atmosphere, it'll evaporate back out from wherever else it's present. And porous materials have long been known to serve as desiccants, especially zeolites, which are naturally occurring desiccants. A zeolite, by the way, means boiling stone. I'm guessing is it Greek, Latin, who knows? Do we have any Greek people here? They'll know. It's Greek. So we set up, just a few years ago, we partnered with a company called Molecule, a project called Aquasorb, where the goal was to develop these regeneration-optimized sorbents, the goal being efficient atmospheric water harvesting. So AWH is water, DAC is direct air capture of carbon, where we wanted low energy of recycling, fast kinetics, and high productivity in terms of how many liters of water you could produce per day. These are the criteria. They're kind of obvious. Must perform well where it's dry, because that's where you need it most. High working capacity, low energy, fast recycling, and a particular type of isotherm called a stepped isotherm. This green isotherm is what we want, where 30% RH, it's below 30% RH. We took the Rolling Stones approach, a screening approach. We turned 80 potential desiccants into 4 Ross materials through a lot of vapor absorption. We worked on formulation. We ended up with cellulomorphs, paper morph composites, Here you see images of the sorbent on the cellulose matrix, paper in other words. And we also developed kinetic modeling methods, thanks especially to my postdoc Andre and student Dan. We were able to develop so-called heat maps to determine the optimal cycling times. And if you actually look here, it's 5 minutes. 5 minutes loading, 5 minutes unloading. And in 24 months, we went from TRL1 to scale up. We did everything up to here and gave them a scale-up recipe, which was water slurry, by the way, and ended up manufacturing in 100-kilogram quantities these sorbent materials. I'll finish off by predicting the future. What is the end game on sustainability? To me, there's only one possible end game, and that is that air will be the source of everything we use. We're in the age of gas. Air contains CO2, nitrogen, water, and oxygen. From those components, you can build all the building blocks you would need to support a chemical industry, but a different chemical industry from the one we have today. It will certainly be sustainable. And when we have that, we'll have a resource, will be air, there'll be pure water everywhere, there'll be food from air, fill from air, and chemicals from air. And it's already in the movies, so it's not as crazy as it sounds. Now, I'm not a betting person. I just lied. I am a betting person. If I were a betting person, I would bet that the person who develops this will be speaking Mandarin, because if you're paying attention to metrics, China is the dominant country in science, but it's also by far the dominant country in material science in terms of outputs. Here you see 2021 data, and the trend is obvious. There's the US, and there's China. I'd like to acknowledge that I definitely couldn't have done this work without my team, which I'm proud is very diverse in culture and gender. Thank you for the opportunity to be here, for the pharma companies that have supported our work, and remind you where you are, right? So we're in the land of Guinness. If you haven't had Guinness in Ireland before, you must taste it, because everybody says it's better here than it is everywhere else, especially the US. So thank you again for the opportunity to be here. And I guess if we have time, it's question time.